no pre-post today.
Do you want me to try to open the memo?
Not gonna work.
Okay.
I had to hide stuff in it. Okay, so what I need to do is just take this. This is the trouble with pre-post. I delete things and
Put your computer up.
yeah, that's good. That up. We got that. We got that, and we are going to go to this.
Okay, you got it.
That's why I didn't. The slide should start. This is slow. Okay, looks good. Okay, so the problem we're attacking today is a very classic so-called Bayes' theorem question. And one of the things about Bayes' theorem is it frightens a lot of students when they say, oh my goodness, it's a Bayes' theorem question. It's really just a conditional probability question. And really, you know, if you think of the logic of how you do this thing, a lot of students can actually do Bayes' theorem questions without even knowing they're doing Bayes' theorem questions. So let's look at you know, what makes a Bayes' theorem question and some of the very interesting implications that come out of a question like this one. And it's a surprising question. And I got to grab my pens because I tossed them in here and didn't really pay attention to where I had them. Okay, so we went through the problem with the mathematized exercise. A rare disease strikes on average 1 in every 1,000 people. A test exists for diagnosing the disease. And it seems like a pretty good test. If a person has the disease, the test is positive 99% of the time. If a person doesn't have the disease, the test is negative 98% of the time. There are a lot of diseases that we are scared silly of, which occur much less frequently than 1 in 1,000 times. There are lots of medical tests too. We can think of the COVID screening tests, which are not near this accurate. So you are tested for the disease. Your diagnosis is positive. What's the probability you actually have the disease? And assume you're a randomly selected individual from those that test positive. Okay, there's reasons why we kind of got to make that assumption. And we've gone through this as a mathematized exercise as to estimate the chance of you actually having the disease. So some may have seen this problem before. It's a very common thing on the first estimate is that you think, I've been tested positive, I'm in big trouble. Okay, there's a high chance I actually have the disease, a reasonable reaction. The actual answer to the question is actually under 10%, and in fact the answer is actually under 5%. Okay, so what we would need to do is make some sense of why does this work this way? Okay, so in order to attack this question, we have to attack it logically, and our first thing we need to do is define our events. And what we need to do is think about how we separate whether or not you have the disease from whether or not you test positive. Okay, so the test is, I won't say it's definitely not independent of whether you have the disease, but it's a separate thing. It's a separate outcomes. Okay. So a person with the disease could test either positive or negative. A person who doesn't have the disease can test either negative or positive. So we separate what the actual situation is from what the test result is. And so what is it we're actually trying to find? What are we trying to find? Okay, in terms of those events, what are we trying to find? A person tests positive for the disease. A is the person, B is the person tests positive for the disease, and we know that that person, you, have tested positive for the disease, and now we want to know what's the probability you actually have the disease. So what we want to find is, let me see if I can make this work good. I'm going to go to the dot camera, I hope.
I think we have a mathematize on this one.
We got to mathematize in that one?
I believe so. Let me see.
Well, will it not allow us to go to the dock camera? Yes, look it, my hand is up there. Yes, we're good, we're good. Okay, so we want to find the probability of A given B. That's the first thing.
Oh. Do we? Maybe Gary is wrong. You. Do you want to do this mathematize? This is asking them to do.
Well, we're going to come up with that one then. And
are you sure? I thought we wanted B given A.
just
no, wait. We want A and B. I forget. Okay, you guys do.
Okay, just think. You've tested positive for the disease. You've tested positive for the disease. You want to know the probability that you have the disease. Right? Okay, let's go back and see. Yeah, you are tested for the disease. Your diagnosis is positive. You don't get a negative diagnosis. You might want a negative diagnosis.
Oh, I see.
Get a positive
I think the problem is I always forget what the little line means. It's like little line, and then which one do you put on which side?
Oh, you're faking it. You know what the line means. Okay. So let's see. We got some nice things there. And, well, which ones of these are we given in the problem and which do we want to find? Okay, let's go back to the problem. And I do ask the question what probabilities are given in the question. Let's try to label everything. And it has a mathematized exercise here. So here's back to the problem. No, it's not back to the problem. I have to go to HDMI.
Okay, should we let them do this?
Let them do that.
Okay. This is also good practice for the test, because, you know, knowing which side the line goes on, that's a question on the test.
Well, it's a question that if you didn't know which...
You definitely are going to do bad on the test if you don't know this. Yeah,
definitely
that's
do
right.
bad on the test, yes.
Right. The converse is not true. Okay. Maybe 2 minutes is too long. Let's do 1 minute.
Well, they do take a little bit of time to think out. But
okay, well,
also
see.
we need to crank it through, too.
We'll see.
We're walking on top of it.
Oh, okay. No wonder.
It'll be calm now.
Okay, do you want to give them more time, or do you want to wrap it up?
I want to wrap it up.
Okay. Okay, time is up. Put in your guesses. If you're not sure, it's okay. Take a stab. I want to see the guesses, and then we're going to learn from there. All right, what are we up to? Okay, here we go. I'm pressing the button. This is your chance to do it. Okay. All right, probability of A. That's the probability you have the disease. That was given in the problem. Very good. Probability of B. What's the chance you test positive? Was that given? So I would say this was not given in the problem. I would say, you know, there's some weird mix of stuff that's given that you could use to calculate the probability of B, but there's no number in the problem. Which of these is the probability of B? None of these things are the probability of B, okay? So you gotta be careful with that. Probability of A and B, also none of these numbers, 99%, 98%, not there. These two are the tricky ones. These two are the tricky ones. All right. One of them is want to find the chance you have the disease given you test positive. B given A, that is in the problem. That one is given in the problem. So the chance you test positive given you have the disease, that's one of these two numbers. Which number is it? Gary will tell you.
Gary will tell you. Okay. Okay. Where are we?
Oh, remember this way.
Let's see. What do
okay.
I want?
Maybe reverse. Let me reverse this. Okay. The doc cam should be coming up. Okay.
Okay. coming up there, I was doing some writing while you were mathematizing. First thing, the first and easy one to get is the probability of A is 1 in 1,000. The probability of a randomly selected person in the population that has the disease is 1 in 1,000, 0.001. Okay, next one I put down is the probability of B given A. Why the probability of B given A? Well, if the person has the disease, and A is having the disease, the test is positive 99% of the time. So that is, in fact, that is the 0.99. We've labeled that there. And then the next part says if the person doesn't have the disease, if they don't have the disease, in other words, the condition is A complement, because A complement is that the person is, the person doesn't have the disease, the test comes back and says you don't have the disease. Okay, and that's 0.98. Okay, so we've labeled all of the probabilities that we have. And now what we want to do is do something with this. We've done our guesses, we've got through that, and we've done that. So what we want to do is work out this table of probabilities here, because there are in fact 4 intersections we want to be concerned with. And notice that again, this 2 by 2 table of what the actual situation is, that whether you have the person has a disease or not, and whether they test positive or not. Any of these 4 outcomes are possible. And what we've got there is a set of 4 intersections, and we have probabilities associated with each of these things. Of course, after the lecture, I'll be posting all the slides if you want to save yourself some notes for the time being. And again, notice that the probability of A is the sum of these two. A probability for A is the sum of these 2 intersection probabilities. Or if you were to say, what's the probability a person is positive? Yes, a B. B either occurs with A or it occurs without A. So how are we going to use this for us? Use this in a productive way? Well, we're going to work this part out on paper. And we're going to start off with a probability tree. Draw a probability tree. Again, when you're attacking questions, problems, whether it's on the test or whatever, sometimes you got to go through different routes as to what's the best way to attack. Sometimes it's a probability tree, sometimes it's a Venn diagram, sometimes it's another approach, and sometimes you got to and sometimes more than one approach works. This is one that a probability tree works very nicely for, because why does a probability tree work so nice here? Well, first of all, we have just 2 branches of whether the person has the disease and the answer is a yes or a no. And the probability of a yes is, and that's the A. Okay, that's the probability of A is 1 in 1,000 equals 0.001. So the probability of not having the disease, that's just the complement of A. That's the probability of A complement. I got to keep remembering to use the little c's. I like primes, but that's me. So, that's 999 out of 1,000, which is 0.999. Yes. And then, given you've got the disease, the person has a disease, there's what the results of the test. So we can say test positive, and the answer is either yes or no. And what we know is the probability of, what do we know? We know the probability of testing positive, given the person has the disease, 0.99. And so if we know that, we also know the probability of testing negative, given the person has the disease. The probability of B given A and B complement given A are in fact complements. And so this is 0.01. Now, if a person doesn't have the disease, and my branches are kind of crooked because I have to wrap around my writing. Again, I could either get a positive diagnosis or a negative diagnosis. And what were we told? We were told the probability of B complement given A complement was 0.98. In other words, the probability of getting a negative diagnosis if you don't have the disease is 0.98. So that is the probability of B complement given A complement. And that little sucker is 0.98. And that leaves us one more probability to calculate here, which is the probability of getting a positive diagnosis if you don't have the disease. And that's 0.02. Now we can go through and calculate all of the intersections by multiplying along the branches. And how am I going to specify this? I'm going to say the probability of A intersect B. I'm showing off my colored pens. Probability of A times the probability of B given A. And I'm going to take the 0.001 times 0.99. I'm not going to work out the number at the moment. There is a number to work out. And this one here is going to be the probability of A intersect B complement. And we're going to take the probability of A times the probability of the B complement given A. And we're going to take 0.001 times 0.01. That's an answer. And we continue to go down. We work out these intersections. This is the probability of A complement intersect B. Is going to be the probability of A complement times the probability of B given A complement. And that's going to be 0.99 times 0.02, and that's a number. We know we can calculate the numbers. That's not a big deal right now. It's just kind of grunt work. What did I have? Oh, I've got one more to write out here. The probability of A complement intersect B complement is the probability of A complement times the probability of B complement given A complement. And so that's going to be 0.999 times 0.98, and that's a number. Okay. So, based on all of this, we are going to come up with this final answer of 0.0472. Where the heck did that come from? Okay, let's just take a look at where this is coming from. I said, well, the probability of A given B is the probability of A intersect B over the probability of B. And you said, well, I know that. I'm trying to find another color. I got it. I got it. It's the probability of A intersect B over the probability of B. Okay, there's the probability of A intersect B. And I need to divide by the probability of B. Where the heck heck is the probability of B? Oh, well, B either occurs with A or it occurs without A. So when I put these two together, add those together, that's going to give me the probability of B. So that's kind of hard to see. So I'm going to write it this way. When I add those two intersections together, that's going to give me the probability of B. So my answer is simply going to be this intersection, the probability of this intersection, over the sum of the probabilities of these two intersections. And so that question that Mihai brought up earlier was probability of B in the question. Well, it was obtainable in the question, but it wasn't directly there. So let's go through our intermediate steps here. Okay, we went through how we got all of those intersections. And then what we do is we get the probability of B by summing these two mutually exclusive intersections. A intersect B and A complement intersect B are the two mutually exclusive intersections. We add their two probabilities, and that gives us the probability of B. So let's take a look at what those probabilities actually are. So here's everything calculated out, and I'm going to just kind of fill these in here. This was 0. Why don't I just look here? It's easier on my neck. 0.00099, and let's see. I want A intersect B complement. And, oh, that is such a tiny, tiny, tiny little number. 0.00001. 4 zeros. So I count enough zeros to pay. This one here, probability of A complement intersect B, comes out to 0.01998. And this one here, this is a big number. Person doesn't have the disease and they test negative. That's most of the people. 0.97903. Of course, those things will, all those probabilities will add up to 1. Okay? But what we were looking at is let's see. Can I move that? Let me just give you a second to make sure everybody's got that down for a second. Or if they want to get it down. And I'm just going to write a little bit more. I'm going to wait and see when people look kind of calm. Calm? Are they looking calm?
I don't think students ever look calm.
They don't look calm?
Calm is after you get tenure.
That is true. That is when you actually are really calm. Everything's scary as anything up to that point. Okay, so I'm just going to take this away for a moment and just go. What did we say? We wanted the probability of A intersect. Sorry. Bad start. Probability of A given B is what we want. We said we're going to take the probability of A intersect B over the probability of B, and we worked out the probability of A intersect B as 0.000999 over the probability of B. And how did I get the probability of B? I added the probability of A intersection B, 0.00099, and I added the probability of 0.01998. And if you wanted an intermediate step, I could give you an intermediate step here. I could have said this is the probability of A intersect B over the probability of A intersect B plus the probability of A complement intersect B. A complement intersect B. Did I get the right one? I did. Okay. There we go. And when we work out that final number, we get that final number. What did we say we were going to get? We're going to get, you can verify it, that comes out to 0.0472, which is under 5%.
Gary, that's remarkably close to 1 out of 21. Did you know that?
It is remarkably close to 1 out of 21.
It's almost exactly 1 out of 21.
Yeah. Kind of interesting.
What are the odds? Maybe
What
there's
are
a
the
nice
odds?
explanation.
Maybe there's an explanation. Okay. Any questions there so far? Questions? Any questions? Okay.
I think there was one, maybe? No?
Yeah.
What do you do with the two values that you're getting?
What are these two values?
Yeah, why are you using two values in confidence?
Why are these two values down here?
Yeah.
Okay.
Why?
Because I wanted to, do you agree that the probability of A given B is the probability of A intersect B over the probability of B?
Yes.
Right. So where do I get the probability of B from? It's not directly in the question. But what we do know is that the probability of B is simply the sum of the probability where B occurs with A and the probability where B occurs without A. Okay? So it's just that decomposition of the probability of B. If you think of a Venn diagram or something like that, you see B will either occur with A or without A. And so if we can add those probabilities for those two intersections together, we get the probability of B. Okay, actually something a little wicked to note. Well, not really wicked. Why is this called a Bayes theorem question? What's really behind a Bayes theorem question? To me, fundamentally, it's about reversing a conditional probability. We were given the probability of B given A, but what we want is the probability of A given B. Okay? And the way we get from the probability of B given A to the probability of A given B is to move through the intersection. And recall, you recall that the probability of A intersect B is equal to the probability of A times the probability of B given A, but it's also equal to the probability of B times the probability of A given B. Oops, that was supposed to be a given sign there. A given B. And so what we are able to do is to move from one conditional probability to the other sort of through the intersection. And you've probably done some Bayes theorem question or two, I think, on the last homework.
Without knowing it.
Without knowing it. Yes, absolutely. Okay, let's just kind of think of where we move next. Okay. Arrive at the final answer, I went through that. Okay, we had those probabilities. So what we want to do is make sense of this example. We drew a probability tree, but here's another way of thinking of this question. And consider a population of 30 million people. A nice round number for the population of Canada, which is higher than that, but let's just think about 30 million people. So if we consider the population of 30 million people, let's consider how they would be distributed. And so what we're going to do is, again, just lay out a table. 30 million people. How many would fall into each of these four intersections according to the probabilities worked out? And there's what our numbers would be like. We would have 30,000 people with the disease, of which almost all of them would test positive. Only 300 of them would test negative. Okay? There'd only be 300 testing negative out of all those 30,000 people with the disease. But consider the people who don't have the disease. That's almost everybody. 29,970,000. You don't feel it's everybody if you actually had the disease, but the point is almost everybody in the country doesn't have the disease. And a heck of a lot of those, 98% of them, end up testing negative, but 599,400 of them end up testing positive. And so this is a false positive. It's a false positive. We call it a false positive because there are people who tested positive that don't actually have the disease. And notice that those false positives totally swamp the numbers who actually have the disease. Okay? Even looking at all 30,000 of them, you have this number so much bigger than this little sucker. So the false positives, they swamp everything. Okay, so again, just to emphasize, the false positives greatly outnumber your true positives there. So what implication does this have for the detection of rare diseases? Very interesting implications. One of the things is that if you know you have a test which is very diagnostic if you have the disease, you may think the probability of a person having the disease is very high. That's a natural intuitive thing. I maintain that one of the things that happens with doctors with experience is they learn that whenever they detect a very rare disease, they have to be very careful to corroborate that with other tests, because your first instinct with experience is you're probably wrong. You're probably wrong. So this is one of the reasons why it's actually very hard to detect rare diseases. Is with experience you realize that rare diseases are almost always a misdiagnosis. Now, can you get refined odds on this? Yes. Follow-up tests, particularly if they're independent tests, but that would be the first thing that, if I was a doctor, I came back and I got this and a person tests positive for this horrendous disease, my very first thought is not to say to them, you have this horrendous disease or you tested positive for this horrendous disease. It would be, do we have another test that we could do to verify or to increase the odds that we're actually correct on this diagnosis? Okay. Okay, so what else did I want to say? Well, I got a couple more things to say, but let me ask Mihai, you had something in your mind.
Oh, I said I wanted to do it with 1,000 people instead of 30 million people.
Oh, well,
What would,
you need a very small country.
yeah, like an island or something, a little island country.
You want to do 1,000?
Yeah, let's do it quick. I'll do it quick.
You do it with 1,000 because he has an interesting
I'll
point
do it.
he wants to make.
I'll do it. I'll do it with 1,000, but I'm gonna do the lazy math way. We got 1,000 people. Okay, here's person number 1, person number 2, all the way up to 1,000. Okay. They all take the test. Wait, we gotta zoom in a bit. This is too. All right, there's 1,000 people. How many people have the test? How many people have the disease? 1. This guy. This guy, sad face. Diseased. All right, how many people don't have the disease? Everybody else. No disease. And they all take the test. Now, let's get a good color here. They all take the test. The test is pretty good. So if one guy just takes the test, he will test positive. He's positive. Right? What about all these other people? Well, there's like about 1,000 of them. And the test is 98% accurate, we said?
98% accurate.
So there's like about 1,000 people. Don't worry about the details. About 1,000 people. 98% times 1,000 people. Well, 2% of them are going to get it wrong, right? So 2%, even though none of these guys have the disease, 2% of them test positive. 2% test positive. How many? 2% of 1,000 is 20 people. So 20 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Am I way off the edge? 19, 20. So this big group of people, even though none of them had the test, look at how many positive cases we got over here. So if you are one of these people, what's the chance you're this poor sucker over here? 1 in 21. One bad. 20 false positives. Okay, these are all approximately.
It's approximate, yes.
Therefore, you got approximately 1 out of 21, 20 plus 1 is 1 out of 21 chance to have it. And this is not right, because I did a bunch of dumb rounding and made the picture stupid. But it's close. 1 out of 21, I think is, I did it on my calculator a second ago, 4.76, I think, percent. Versus the real answer is 4.72%. This is the real answer. So it's close. This is how I think about it. That's how I did it. Okay. There's my Mihai's dopey cartoon of the day. Okay, I'm done.
Okay. Give me a second here. So I want to leave one kind of slightly more challenging earn question with you. And now we have 2 earns. And one has 3 red and 2 white balls. Earn 2 contains 1 red and 4 white balls. And earn gets selected at random. And 2 balls are randomly selected with replacement. And then the question is, what is the probability that both are red? But the more interesting question is this one here. If the 2 balls randomly selected with replacement were both red, what is the probability that earn 2 was chosen? So why is this actually a Bayes' theorem question? Well, I will tell you right now that, again, many of you could do this without knowing it's a Bayes' theorem question. But the point is that if earn 2 is chosen, and remember this is with replacement, it's very easy for you to calculate the probability of getting 2 reds. Similarly, if earn 1 was chosen, it was very easy for you to calculate the probability of 2 reds. But given that you get 2 reds, does that cause you to revise your probability, or does that allow you to revise the probability that earn 2 was chosen? Remember, initially, the prior part of the experiment, it was a 50-50 proposition here, right? That said the 2 earns were chosen at random. There could have been other probabilities, but the point is that this particular one, they were chosen at random, so it was a 0.5 probability for picking earn 1, 0.5 probability for picking earn 2. But given you get 2 red, what's the probability that was actually earn 2 you chose? And one of the things as you're looking back on this problem is you realize it's actually easier to get 2 reds with earn 1 than it was with earn 2. And so that seems to give us some information as to, at this point, would you want to bet that earn 2 was chosen as a 50-50 proposition, or would you want to revise that estimate based on this updated information of what you got from the randomly chosen urn. So I'm not going to go through this question, but I will just leave it for your things, and those are the answers. Okay, so we see that in fact we revised that probability that it's earned 2 from 1/2 to 1 out of 10. And that's all we've got to say for today. Mihai, did you have anything? Okay. You all have a good weekend, and we look forward to seeing you Monday.